Hello, ladies and gentlemen. This is Mr. Collier, and this is one of my favorite topics to talk about during our physics quarter. And it is great. We're going to talk about gravity. And this is something that, we all are familiar with, and we have a good sense of what it is, and it just really makes it fun. All right, let's put a little corner picture here because I just love gravity. So I'm going to put a little ground. And I got a big old tree here, and this tree has some branches, and there's a little knot right there. And sitting here is a stick figure of Isaac Newton. There he's smiling, there's his feet, and there's his hand. In his hand he has a big book. And hanging from this tree, of course, is a very poorly drawn apple. And at some point maybe that apple will fall to the ground and help old Isaac Newton out. But let's get on with the serious part. The first thing we're going to talk about is we have to be very formal here, and we have to say, write down about the law of universal gravitation. That's very formal sounding. Law of universal gravitation. Trying to spell it there. I'm struggling as I try to talk. The law of universal gravitation. You have to have a formal voice when you say that. All right. This is important. Watch this. I almost never do this in science. I'm going to use this word, all. Oh my gosh, we never say all. I am here today. All objects in the universe. Oh my gosh, you guys, that is so amazing. All objects in the universe attract each other through gravitational force. I'm going to finish writing that. Through gravitational force. And just parenthetically, I'm talking about gravity. Gravity is a force. Now this is amazing, you guys. All objects, everything in the universe is attracted to everything else in the universe via gravity. That means the pencil you're taking these notes with is attracted to the desk that you're sitting at, or to your nose, or to the chair across the room. Everything is attracted to everything else through gravity. It's amazing. It just blows my mind. All right, a couple things we've got to talk about with gravity. Write this down. Gravity depends on two things. You've got to write these down. Number one, gravity depends on the size of the mass. The size of the mass. Now this is really obvious to us. I mean, when you're standing somewhere, you're in your kitchen, and you're standing next to the fridge, you don't just fly into the fridge because of gravity, and yet if you jump up, you fall down very quickly towards the earth because the earth has so much more mass than your refrigerator that it pulls you in, but of course the refrigerator does not. So gravity depends on the size of the mass. Let's finish that S. And as an example, I'll just say as mass goes up, gravity goes up. And we talk about things like the sun having a ton of gravity, or a lot of gravity, and that's the reason why, because the sun has so much more mass. And gravity depends on another thing, number two, the distance between the masses. The distance between the masses. So you can have a huge object out in the universe that is huge and has an amazing amount of gravity, but if it's too far away, we won't feel it because it's too far away. So let's put a little detail there. As distance goes down, gravity goes up. And as distance goes up, gravity goes down. So, the reason that we are attracted to the Earth and keep our feet on the ground is because the Earth is massive and is really close to us. The reason that we don't kind of get sucked off into our huge sun is that although it's massive, it's a long ways away, and it keeps us from flying out that way. So gravity depends on the size of the mass and the distance between the masses. So that's really important to know. Now, let's go on to a new term that you may have heard before, and this is something called free fall. Free fall. You've probably heard of this before. Free fall is the situation when gravity is the only force acting on an object. And we'll talk more about this in class. So we often think of free fall, maybe a parachuter is jumping out of the plane and they'll do some time of free fall when really the only thing that's really acting on them is gravity. They're just falling. They haven't popped the parachute yet. That is free fall. All right? The next, let's talk about, and this is an amazing thing, this is the acceleration due to gravity. Gravity accelerates things. The acceleration due to gravity is equal to, and this is a very famous number that you should just memorize now because, one, it'll impress people at the dinner table, and two, you'll need it all the way through high school and college. The acceleration due to gravity is 9.8 meters per second squared, or 9.8 meters per second. And this is an amazingly famous number. So the acceleration due to gravity is 9.8 meters per second squared towards the center of the Earth. And I'll show you a very fun video that you'll really enjoy that talks about this very thing. Anyway, I like it a lot. Now, in class, we've talked about mass, and that mass is the amount of matter on something, and we've sort of bantered around the word weight. And here I am, for the first time, officially going to give you a definition of what weight is. Weight is the force of gravity acting on an object. Weight is the force of gravity acting on an object, and it is measured in newtons. Wow. So when someone says, how much do you weigh? You should give it to them in newtons, right? And the thing about weight is that your weight would be different on Mars or the moon because they have a different amount of gravity. And we will talk about that in an example in just a moment. Next, we know this already. Let's talk about what mass is. Mass, and you've already done this definition. Let's do it again. Mass is the amount of matter, and the very unofficial firm word for that is, stuff, the amount of stuff in an object. And of course, if you have, a bowling ball here on Earth and you took it to the moon, the weight would be different because gravity is different on the moon, but the amount of stuff would be the same. So that would be the same on the moon as here. So, example. Earth's gravity is equal to 9.8 meters per second squared. We wrote that just up there. And if you had an astronaut who had a weight of 66 kilograms, which is a very average weight for a person. And let's divide the page here a little bit, move over, and let's just state here that the moon's gravity is 1.6 meters per second squared. Okay? And if you had an astronaut on the moon, because mass is the amount of stuff in it, that astronaut would have the same amount of stuff, and they would still have a mass of 66 kilograms. Okay, so we got gravity on the Earth is 9.8 meters per second squared. Gravity on the moon is 1.6 meters per second squared, roughly a sixth. All right, so let's calculate weight. Weight on the Earth, and weight is a force, so it is equal to the mass times gravity. Okay, that's M and that's A. Force equals MA. There you go. So our weight is equal to 66 kilograms times 9.8 meters per second squared, and that means our weight is equal to 650 kilogram meters per second squared on the Earth for that 66 kilogram astronaut. On the moon, again, we're going to say weight is equal to mass times gravity. Weight is equal to 66 kilograms, because again, that astronaut isn't made of any less stuff up on the moon, but the gravity is less. Gravity is 1.6 meters per second squared. And so when we get the weight of the astronaut up on the moon, it is only 110 kilogram meters per second squared. So when you take something to the moon, it still has the same number of particles that make it up, the same number of atoms and molecules, but its weight is different. So weight depends on the amount of gravity. Mass is the same no matter where you are. This concludes our notes. I hope you found these helpful. Thanks.